Welcome to the last lecture of video course on tribology. So, final lecture. We are going to complete bearing design or hydrodynamic bearing design based on short bearing approximation, assuming bearing length is much shorter than diameter of bearing. Much shorter means maybe say 0.25 times of the diameter. And most often in the present situation we prefer short bearings. Even in our previous lecture it was pointed out increasing length is going to increase load carrying capacity and sensitivity of the length is much larger, much stronger, but increasing length has some problem like a misalignment, more heat dissipation or more heat generation, increase in a temperature rise, increase in a coefficient of friction. So, we need to account this when we are talking about the design. It is not only the load carrying capacity, we need to think from temperature point of view, coefficient of friction point of view, and again we are always aiming for the miniaturization. Shorter is the better, that means smaller size is the better. That is, from that angle length need to be reduced. So, we are continuing with first slide from the previous lecture. We say attitude angle, which was shown or is mentioned in previous lecture, can be given as tan inverse of 1 minus epsilon square root of that divided by epsilon. If using this relation we can find out attitude angle. And once we know the eccentricity and attitude angle, we say that shaft center is fixed, is been located, and it shows that when you try to plot this E versus attitude angle, or say that epsilon versus attitude angle, what we are going to get, we can change eccentricity from 0.01 to say 0.99 and try to find out what will be the attitude angle. This is turning out to be when eccentricity ratio is very low, attitude angle is very large, it is almost 90 degree. When eccentricity is very high, attitude angle is much smaller. In practical situation, we do not want much smaller attitude angle. That is why from designer point of view, I will keep eccentricity ratio up to 0.88 or say 0.80. More than that will not be recommended, because we know there will be some sort of fluctuation in the load that may increase the eccentricity ratio. So, from design point of view, I will prefer 0.8 and minimum value as a 0.5 or 0.4. That means, this should be the operating zone for the bearing under operation. Reason being, lesser the attitude angle, more will be instability of operation. That is why whenever the attitude angle is much larger, eccentricity is much smaller, we change the bearing, we reduce the bearing length, we make unnecessary grooves in the bearing, so that eccentricity ratio is greater than 0.5 and bearing is going to be a little more stable. And this is often the case with bearing operating under high speed applications, because we know that as speed is increasing, load carrying capacity of the bearing is going to increase, and if the load carrying capacity of bearing is going to increase because of the increase in the speed, eccentricity will decrease. Eccentricity will decrease for the same equilibrium the load, and that decrease in eccentricity is going to increase attitude angle, which is unfavorable. That is why many times for high speed operation, we do not go ahead with the cylindrical bearings, we go ahead with the offset bearings, we go ahead with elliptical bearings, four-lobe bearing, we try to distort the bearing clearance, we try to reduce the bearing clearance and try to increase stability, increase eccentricity in those ratios in those zones. But that is totally a separate subject for us. We are going to discuss about the bearing design based on the short bearing approximation, and this is gives an indication. Try to keep eccentricity ratio maybe say 0.4, more than 0.4, but lesser than 0.8. If any time bearing eccentricity is increasing beyond the 0.8, try to modify the design, change the parameter. If it is turning out to be lesser than 0.4, try to change the parameter, increase this eccentricity. This should be more operating zone for the bearing. Now, we discussed about the load carrying capacity. We can use a short bearing approximation to find out that. And in addition, mention the bearing length should not be extended because that is going to increase the friction force. Question comes how? That is what we are trying to find out, how to drive the friction force. We know we have discussed Petrov equation, but for the bearing we are saying that is inaccurate equation. I will demonstrate that using after deriving this friction force formula. So, friction force will be depending on whether there is a metal to metal contact, and we know for hydrodynamic bearing there will not be any metal contact. That means there is only shearing of liquid lubricant. That shearing can be shearing the stress can be given by using this relation. It is eta, higher the viscosity, higher will be shearing, higher the velocity, higher will be the shearing, lesser the film thickness, higher will be the shearing. Then comes the pressure gradient and h by 2. To find out friction force, naturally we need to integrate the shearing stress over its area, and that area is r d theta because polar coordinate into dz and axial length. And we have already demonstrated that bearing effective bearing is only half of the bearing. That is why the integration for the theta will be theta equal to 0 to theta is equal to pi. We again mentioned about the z, that at the mid plane we are assuming z is equal to 0, that means extreme will be minus L by 2 to plus L by 2. L is a bearing length. Once we integrate this, what we are going to get this expression. It is interesting to note that F friction force itself depends on the load. This is a W sin phi. Whatever the load, applied load, that is going to affect the friction force, maybe to a lesser extent, but it is going to affect friction force. And we try to see what is this friction force relation, that is a W sin phi, that can be given in terms of other parameters like eta, u, L, cube, c square, and we are able to see the number of terms are common in these two. So, to simplify it, what we can do, we can take some common terms and compare this term, first term, with the second term. If the second term is negligible, for our simple calculation we can neglect this term, but if it is not negligible, then we need to account slightly more complex problem. And when we talk about the Petrov equation, the Petrov equation can be derived from this relation itself. If I use epsilon is equal to 0, we are going to get the Petrov equation, same which we have derived in our lecture or earlier lectures. No, this gives, when I am using the epsilon equal to 0, that is giving the Petrov equation, but is the situation where there is no eccentricity, so that the shaft and the bearing surfaces or centers are coinciding, there is no load carrying capacity of that bearing, how friction force will be generated? Friction force cannot be generated. That means Petrov equation, which is predicting the friction force, because of that is inaccurate. No force, no normal force, but still there is a friction force. That's not a good option. That's why we say that Petrov equation cannot be used for the bearing design. But with a modification, when we say using an integration of shear stress can provide a good results. Of course, it is based on the short bearing approximation, so it cannot be 100% reliable, but it gives a reliable results. Now, as I mentioned, there are number of terms common in these two relations. This expression we can take common term. This common term turn out to be 2 pi eta u L r divided by c, and in bracket also in the square root 1 minus epsilon square. So, this will be 1 plus epsilon square into L square divided by 16 L r square. So, if I assume 4r square is equal to d square, that means L by d square term is coming here, and we are talking about the short bearing approximation. So, length may be equal to 0.25 times of the diameter. So, what will turn out to be? This L by d square will turn out to be 0.25 square. We know eccentricity may be 0.8 maximum value we are choosing. So, 0.8 square will turn out to 0.64. So, 0.64 into 0.25 into 0.25 divide by 4, that means 0.25 into 0.25 into 0.25 into 0.64 will turn out to be much lesser than 1. It can be neglected for our simple calculations. For detailed analysis, it can be incorporated. For simple classroom calculation, it can be neglected. That is why in our calculation, we are going to treat this f, or we are going to write f or estimate f as 2 pi into eta into L into r u into r divided by c and square root of 1 minus epsilon square. So, this is a simple friction expression we can be utilized. We can utilize this. Now, we were discussing on the friction force from temperature point of view. We want to estimate temperature, so that we can modify viscosity, we can properly estimate the load carrying capacity of bearing, as viscosity is going to affect load and temperature is going to affect viscosity and friction is going to affect temperature, and this is a common chain. So, naturally we required a good approximation, do a complete iteration procedure to find out what will be the final result. Perfect combination of temperature, viscosity, friction force and load. That is why we required a flow rate also. If there is a possibility the temperature of the heat generation is there and it is getting convected and conducted. Simpler one is assume the conduction is 0, that is going to give slightly conservative design to us, but that is fine for us. And to proceed in that direction, we required what is a flow rate. We discussed earlier, if there is a hole arrangement or slot arrangement, we can estimate what will be the flow rate, that is a QP. In addition to that, flow generally occurs because of the velocity. That velocity, the circumferential flow, can be given by this relation, that is a q theta flow rate passing from any location, theta location can be given in this term. Again, in this situation also this term is almost negligible compared to this dominating feature or dominating term. So, for our calculation we are going to neglect this second term, we are going to account only first term. And this overall leakage, we say that when we are as you finding the flow is coming in, maybe theta is equal to 0, theta pi film thickness is minimum, the most of the liquid is leaked out, not most of the whatever the liquid is some portion of that liquid is leaked out and remaining portion is getting recirculated. So, we require this leakage rate, that is going to give us cooling effect, because this liquid will be again cool and come back or can be returned back using the pump arrangement, and that Q leakage as it is happening because of the hydrodynamic action can be given in other form also. We say that instead of writing Q leakage I can write QH due to hydrodynamic action, and what we say that here the feed pressure flow due to feed pressure will be QP. Overall may be a combination of QH plus QP. There will be some sort of disturbance when the pressure comes, there will be slightly decrease in QH or the overall flow rate. For time being we are neglecting that. We are saying the QH can be calculated by integrating over the length. For two situation, what is the exit condition, that the Q theta is equal to pi, and what is the entrance condition, that the theta is equal to 0. So, theta is equal to 0, theta is equal to pi, that difference is going to give us what will be the leakage from the bearing QH coming out of the bearing, which is going to give us cooling effect. And in fact, it has been observed 80 to 90% heat is being carried away by liquid lubricant, which are going to get leaked from the surface. So, this is going to give us a reliable results, reliable in the sense 80 to 90% results. When we integrate it, we know that u is not depending on the z, h is not depending on z. So, it will be turn out moved out, and the dz will turn out to be complete length, that means L by 2 minus L by 2, that minus will turn out to be positive, that is L by 2 plus L by 2 is equal to 1, that comes out here. This will be maximum film thickness, or we say that q as that will be h as at theta is equal to 0. So, this will be C into 1 plus epsilon. This point h will be minimum. So, that will be C 1 minus epsilon, and when we arrange it, is turned out to be q h is equal to velocity, clearance, eccentricity ratio into length. It depends on all, and this is a volume flow rate. We can find out the relation here. This is the meter per second, meter. So, that will turn out to meter cube per second. But if we are interested in mass flow rate, what we are going to do? We are going to multiply with the density, that is generally kg divided by meter cube, and meter cube will be cancelled out, they will turn out to be kg per unit second, the mass flow rate. This is important for calculating the temperature rise. So, finding the temperature rise, we need to find out what will be the heat generation, that the friction force into velocity is going to give us what will be the generated heat, and that is going to be carried away by a liquid lubricant. Assumption, we are saying that there is no much conduction and most of the heat is being convected from using the liquid lubricants. So, we require a thermal equilibrium, we say rate of heat generated is equal to rate of heat convected by oil. Rate of heat generation can be given it as a F into U. F is given like this, say 2 eta U L R into pi divided by C square root of minus epsilon square, that is being given over here, and there is a velocity that is can be given as a 2 pi r into n, also the pi d n is equal to as a m Cp, that is a mass flow rate, specific heat into temperature rise for heat convection, and that is going to give us the total temperature rise as equal to this relation. Now, this temperature rise is going to depend on viscosity, and viscosity is going to depend on the temperature. That is why we are keeping close loop of temperature and viscosity. Then it depends on radius, very sensitive, temperature rise is very sensitive towards the temperature radius, larger the radius, more and more temperature rise, and it depends on the clearance, larger the clearance, lesser will be the temperature rise. This is overall relation for temperature rise, we can calculate using these relations, and of course, we derived the m as a mass flow rate in previous slide, that can be incorporated over here. Mass flow rate which was derived in previous slide, it was given as rho u c, that is clearance, epsilon into length. Substitute, rearrange. After substitution, we are rearranging this, what we are going to get, this is a ratio r by c square, that means and this is related to the liquid specific heat and density, this is speed and viscosity. So, larger viscosity, larger temperature rise, larger than this ratio r by c, larger will be the temperature rise. Larger the density, which is generally not happen by and large, this rho and Cp will remain constant, is not going to much affect this, whatever the temperature is, if I change the liquid lubricant, is not going to change because of this product, but because of viscosity it will change. Now, we can think what we have done, we have derived the relation for load, relation for flow, relation for friction, relation for temperature, and flow incorporate the relation of temperature involves a relation of the flow. That is why we say how to do design. First, guess eccentricity ratio. Eccentricity ratio being guessed maybe at 0.5 will be an initial approximation. We know minimum value 0, maximum value 1. I will take 50% of that. 50% is a epsilon ratio, epsilon is equal to 0.5, our eccentricity ratio as a 0.5. That is an initial guess, we need to go ahead with that. Once we know eccentricity ratio, we can find out the load, we can find out the friction force. Flow has been already been incorporated in temperature rise. So, we do not have to calculate separate flow rate. If there is no flow due to supply pressure, obviously supply pressure is 0 in those situations. Otherwise, when we are supplying with some feed pressure, naturally flow rate need to be counted and separately accounted for the temperature rise. So, for present case, we are calculating the load for given or estimate eccentricity ratio, estimate the friction force and temperature rise. Once we know the temperature rise, we need to use lubricant viscosity relation of the temperature viscosity relation to modify the viscosity. Once we modify, again we need to go to the calculation, and we can think about eccentricity calculation, load calculation, friction calculation, temperature rise. So, it will be continuously iterated. That is why we say repeat steps 1 to 3. So that average viscosity and load are going to converge. After that, even you repeat, results are not going to change. That is a convergence. It may be 3 step, maybe 5 step, maybe 7 step, maybe 10 step, depending on 15 steps, depends on your initial approximation. And of course, for most of the complicated situation, we use this procedure to provide initial good approximation. In other words, if I use a finite difference method, and start with some arbitrary eccentricity ratio, it is going to take long time to converge. But if I use this kind of short bearing approximation, estimate the results and use those results as input to the finite difference method, number of calculation will reduce significantly, and overall there will be better, overall there will be a lot of gain on that. So, what we say, if we assume some eccentricity ratio, substitute this, find out the load carrying capacity, that is one, find out the friction force, then find out the temperature rise. Once we know the temperature rise, delta T, modify the viscosity, that is what we have mentioned. There are 3 steps, eccentricity is a guessing, so that does not require any calculation as such, it is the guess. Then load calculation, friction force calculation, temperature calculation, then finally viscosity calculation, and this viscosity is going to be input to the load. Naturally, it requires iterations, it requires overall iteration to converge to one final solution. And to demonstrate this procedure which has been discussed earlier, let us take one example. What this example means? Say in this case, we are trying to find out number of bearing parameters. Says determine, estimate or calculate minimum film thickness, maximum pressure, coefficient of friction. We have not done coefficient of friction, but we know if we are able to estimate friction force and we know the normal load, take that ratio F by W, that is going to give me the coefficient of friction. And this has been what we say, that it has been required to estimate all this when bearing is supporting 600 Newton load at the rotational speed of 2000 RPM. Rotational speed has been defined, applied load has been defined, shaft diameter is a 40 mm, that is similarly bearing dimension also will turn out to be almost 40 mm. Assuming the bearing length is a 10 mm, then the L by D ratio is a 0.25. Oil viscosity, the room temperature has been defined as a 15 millipascal second. Beta, that is a constant for calculating the viscosity at any temperature rise, is been given as a 0.029, and radial clearance C is being defined as a 20 micron. That shows clearly the radius of the shaft is 20 micron, 20 mm, and clearance will be 0.1% of that, that is a 20 micron. So, we are following that same scheme. The radial clearance is a 0.1% of radius. Now, some important calculation, we say that U will be utilized again and again. So, instead of directly calculating in a formula, you separately calculate what is a U, and that is a calculator pi dn. We try to find out that is a 4.19 meter per second, or say 4.2 meter per second. Then another factor, U L cube pi 0.25 divided by clearance square should be calculated separately, because we are going to do iterations. We do not know exactly what will be the eccentricity ratio. We are going to assume and calculate W based on that. Once we calculate W, we are going to find out the friction force, temperature rise, and viscosity based on that. Again, that means there will be iterations. That is why we use this calculation separately. U L cube pi 0.25 divided by c square, this is not going to be calculated again and again. We can directly use this factor, that 8227 meters square per second directly. Same way, for the friction force, we use a separate factor, that is a 2 pi L into R into pi divided by c square. Again, this will not be calculated again and again, but friction force will be calculated again and again, because we require iterative scheme, we require perfect iterations to evaluate what will be the friction force. To demonstrate it, as I say, that first approximation for me will be eccentricity as a 0.5, maximum value is 1, minimum value is 0, I will take 1 plus 0 divided by 2, that will turn out to be 0.5. I will be using that as a first approximation. So, when epsilon is 0.5, what we are going to get W as a 118 lower. I do not have any other idea, we can use some sort of interpolation, but for that purpose what we require, again the mean value. For interpolation we require two values at least, first load and then subsequent second load. So, what do? We know maximum value of eccentricity is 1, this epsilon minimum mid value is a 0.5, and we are not getting the desirable load carrying capacity, which is 600 Newton, and what we are getting is 118 Newton. What I will do? I will again do 0.5 plus 1 divided by 2, take a mean value, that is turning out to be 0.75. So, eccentricity 0.75, what we are going to get W as a 562 Newton. Now, I can use some sort of interpolation to evaluate, or I can find out again averaging value 0.75 plus 1 divided by 2, I can go ahead with that, but that rough approximation says that generally we do not recommend more than 0.8. So, I am just taking the value as a 0.8, epsilon value as a 0.8. I want to find out whether the load carrying capacity is really exceeding 600 Newton or not. So, eccentricity 0.8, what we are going to get? W as a 900 Newton, which is a 50% higher than this. Naturally, we can decrease this, take intermediate value of these two, but we know viscosity which has been used in this calculation is a 15 millipascal second, and that is happening at the room temperature. We are not calculated at the operating temperature, and viscosity is going to be lesser than this at the operating temperature, that is going to reduce the load carrying capacity. So, for time being we are saying this, okay, let us assume eccentricity is a 0.8, calculate W, calculate friction force, find out the temperature rise, and that is turning out to be 8.65 degrees centigrade. Now, what is the next step? To find out what will be the viscosity for this. Of course, we have used this relation, which is a factor 1, how it has been utilized, factor 2, how it has been utilized. We are not doing this calculation again and again, we are simply substituting the factor. We know epsilon is going to change, viscosity is going to change. That is why, except these two, we are assuming one constant factor. Similarly, for friction force, viscosity is going to change, epsilon is going to change. So, keep apart from these two things, all other will be constant. So, that is why the factor 2. This is required for simple calculation to reduce the efforts. And temperature rise again can be given. In this case, again we can find out the viscosity, speed is a constant, 4 pi is a constant, R by C is constant, rho Cp is constant. We can take this as a factor 3. And here nothing has been mentioned, but we are using the word density of the liquid as a 860 kilogram meter cube, and Cp as a 1760 joule per unit kilogram per centigrade. This has been utilized, and most often for liquids these are the results. For the liquid lubricant these are the relations, obviously these are the parameters for liquid. So, we can substitute, we can find out another factor 3 in this case, which will be 4 pi into n into r by c square divided by rho C p, that will be remain constant, and after that we can we can keep changing eta and epsilon to find out final temperature rise. Now, once we know the temperature rise, we can use this to find out what will be the viscosity, what will be the operating viscosity. That is, viscosity is given as, this is defined, eta in is already known, beta is defined, delta T we calculated, that is going to give viscosity as 11.7 millipascal second. In our calculation earlier, we assume this is a 15 millipascal second. So, almost 20 to 30% change in viscosity. Now, we need to substitute this value, this viscosity in the load. Say for epsilon is equal to 0.8, with the modified viscosity what we are going to get W as a 703 Newton. Earlier we got 900, applied load is a 600, 50% variation, but after incorporating this viscosity change, what we are getting W as a 703 Newton, which is still higher than applied load. Naturally, we need to change eccentricity, we need to decrease eccentricity ratio. For here, for this kind of eccentricity and viscosity, what we are getting F as a 5.13 Newton. Calculate temperature rise. So, it has reduced from 8.65% to 6.75%. I am sorry, not percent is a 8.65 degrees centigrade to 6.75 degrees centigrade. It is reduced. Now, at this temperature, we will again try to find out what will be the operating viscosity, and that is slightly more. That is turning out to be 12.3 millipascal second. We did calculation for 11.7 pascal second. Naturally, this viscosity W will be on a higher side. That is why now is the time has come to take an average 0.75 and 0.8, take an average of that and now to be 0.775. For time being, we are taking eccentricity ratio as a 0.78. So, 0.78. When you calculate, this temperature rise will turn out to be 7 degrees centigrade. Calculate load at this is turning out to be, fortunately, it is turning out to be 599.1 Newton, very close. We know we have done approximation. If we want, we can keep slightly more load. We can increase this 0.78 from 0.78 to 0.79. And keep a higher load, or depends what we want. In this case, friction force is almost the same, temperature rise is also almost coming to the points around 7 degrees centigrade. Viscosity, operating viscosity is turning out with 12.2 millipascal second. This is a fine design for me. Or we say if you want to go for the finite difference method, this design is going to give reliable results. Or if we assume that load carrying capacity estimated by short bearing will be slightly higher, then we can think about 0.7 also, 0.79 also, which will give roughly maybe say around 640 Newton load capacity. Applied load is only 600, we say okay, that is fine for us, we can go ahead. So, this is a word which is the how we do calculation. Next comes how to find out attitude angle. We are following a short bearing approximation. We have calculated epsilon as a 0.78, substitute this value, find out attitude angle, and attitude angle is turning out to be 32.2 degree. That is fine. So, eccentricity 0.78, attitude angle 32.2 degree. So, this is all about, but problem. What we have asked in question, find out minimum film thickness, find out maximum pressure, find a coefficient of friction, and we have not discussed those things till now. This is a first step. Locate the shaft, find out the eccentricity and attitude angle, and after that do remaining calculations. So, this is we have completed, we have converged to the final result, eccentricity 0.78, attitude angle 32.2 degree. Now, time has come to find out the minimum film thickness. We know clearance. Film thickness can be determined based on epsilon as a C minus in bracket 1 minus epsilon. Substitute this value, 20 micron is the radial clearance, 0.78 is the epsilon value, this turning out to be 4.4 microns. Question comes, whether we have done everything right? We are talking about hydrodynamic lubrication, and we know hydrodynamic lubrication we need to will be valid for the specific film thickness by and large more than 5. If surface roughnesses of shaft and bearing surfaces are given to us or provided to us, we can find out the specific film thickness using this relation, that will be ratio of minimum film thickness to the composite surface roughness. Now, if I assume roughness of the shaft is a 0.4 micron, maybe on higher side, and bearing maybe even 0.6 microns, take a composite one and find out what will be the composite surface roughness. If this ratio is turning out to be more than 5, we say okay, hydrodynamic lubrication is fine, bearing design is as per the hydrodynamic lubrication, there is no problem. If that is not the case, then we can think about adding hydrostatic lubrication. We can supply pressure that is going to reduce temperature, and that is going to reduce film thickness or reduce eccentricity. When epsilon is decreased, naturally H min is going to increase. So, that way feed pressure is going to increase film thickness, is going to bring we say mixed lubrication domain to hydrodynamic domain. So, we can do calculation, when we do calculation we find out whether everything is fine or not. If it is not, then we should use some sort of feed pressure to supply liquid to cool the liquid to cool the liquid lubricant or reduce the temperature, make it to a effective viscosity more than what has been estimated and get the results. So, this is the film thickness. And next comes the maximum pressure. And to find out the maximum pressure, this is a short bearing approximation. We know maximum pressure will occur when Z is equal to 0. That is a condition which we have used to drive this relation. Then the mid plane dP by dZ will be equal to 0. Now, we have used Z equal to 0, but we need to find out at which angular position maximum pressure is going to be there or maximum pressure will be generated. On pressure profile, what will be the location of maximum pressure, that means theta O max. Theta O because of short bearing, or theta 0 as a we are using a short bearing approximation. So, start with the pressure relation first. We say that this is a pressure relation. We say that maximum pressure will occur at Z equal to 0. Substitute this, rearrange this, and after that differentiate with respect to theta. After differentiating with respect to theta, equate to 0. That is going to give us theta for maximum pressure. Once we now substitute those values over here and find out maximum pressure. In our case, this been done and we find this location of maximum pressure theta 0 max depends only on eccentricity ratio. That is what shown over here. It is a 1 minus in a square root of 1 plus 24 epsilon square divided by 4 pi. Now, we know this will be always greater than 1. That means theta is going to be greater than 90 degree. This is going to be negative. Now, epsilon can be 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8, whatever you take, this will be negative. If this is a negative, overall will turn out to be negative. Sorry, this will be more than 1, and if it is more than 1, 1 minus more than 1 naturally will be negative. That is why the theta will be always greater than 90 degree. In present case, This is turning out to be 105.4 degree, and this is different than theta is equal to pi. This is different than theta is equal to pi. That means location of minimum film thickness is different than location of maximum pressure. Otherwise, in many books it has been confused, it has been treated the maximum pressure location and minimum film thickness location are the same. It is not the way. Their locations are different. Now, based on when we substitute this value theta O max in this expression, what we are going to get maximum pressure as 724 bar. Not very high value, it is well within permissible limit. Megapascal, it is only 0.724 megapascal. It is not very big up, and there is a big quantity or larger. Any material can be used. Any bubble material can be used in this situation. Now, final comes the coefficient of friction. We needed to find out coefficient of friction. We know what is the friction force. We know what is applied normal load. Take a ratio F divided by W. That is what is going to get. We are going to get that is a 0.0086. This is very low coefficient of friction. 0.0086, almost negligible friction. That is why the hydrodynamic bearings are most popular. Whenever we require good comfort, good damping, low coefficient of friction, zero wear, hydrodynamic bearings are on the top place. Now, what we can do to find out if length is doubled, what is going to happen with these parameters? Just now, of our present case, we took length is a 0.25 times of the diameter, but if we are going to increase this length, we will say double the length. Instead of 10 mm, we can think about 20 mm. What is going to happen? That is shown here. The same data which we define, the same viscosity, same load, same speed, same everything, right. Now, only the variation is bearing length. Instead of 10 mm, we are considering as a 20 mm. If we do that, again we need to assume as a first step what is the eccentricity ratio. We need to guess. As I mentioned earlier, for me simple guess is summation of 1 and 0 divided by 2, that is an average value at the first step, and that is epsilon giving as me as a 0.5. This is turning out to be 943 Newton. Now, I can take again average 0.5 plus 0 divided by 2, that is epsilon as a 0.25, but we feel epsilon lesser than 0.4 should not be recommended. Well, in this case, we have recommended a 0.45 minimum value. It should not be lesser than that. Otherwise, we need to change the design. So, epsilon, if I assume as a 0.45, we can find out the load as a 740 Newton, which is a more than 600. We can reduce it further, but what we want to do a calculation. We know this 741 is at the 15 millipascal second viscosity, and if we account the temperature rise, this will be lesser than that. Maybe viscosity will be 12 millipascal second or 13 millipascal second. So, this will be reduced. So, for time being we can assume the eccentricity initial approximation as a 0.45, calculate the friction force, and friction force calculation gives the result as 8.84 Newton. Based on that, we can find out the temperature rise, that is turning out to be 10.33 degrees centigrade. Based on this, we will modify the viscosity. This is a 15 millipascal second, temperature rise is 10.33 degrees centigrade, and beta is given to us in an example or in a question. So, based on that, what we can find out the viscosity, that is turning out to be 11.1 millipascal second. We substitute this value to find out what will be the load carrying capacity. Now, with this viscosity, eccentricity 0.45, load turn out to be 548 Newton, which is a lower than applied load. I can change viscosity, I can change eccentricity immediately here. Other one is that calculate again the friction force, recalculate temperature rise, recalculate viscosity, and again see whether that is going to increase this load carrying capacity reaching to the final value which we require. If it is the case, we say that we do the calculation now, find a friction force, evaluate temperature rise. Based on that, find out the viscosity, that is instead of 11.1 now is turning out to be 11.9 millipascal second. Substitute, W is turning out to be 588 Newton. Again we can do calculation, but we know this eccentricity is not going to increase to the 600. I can think about this eccentricity is a 0.46, and 0.46 also can give me some result which is slightly more than that. Now, it is my choice whether I go for slightly higher value or converge itself here. Instead of 588 is a valve within 5% of the load, I can converge it, or we can think about slightly more than that. So, when we are talking about the epsilon as a 0.46 and the load carrying capacity is of 606 Newton, F is 6.9 Newton. So, I can find out, I can close this example with eccentricity as a 0.46 or eccentricity of 0.45. Both options are open to me. This is giving me high load carrying capacity, that is giving slightly low load carrying capacity. So, from say the conservative point of view, I can choose this, or for the continuity we say now we do not require too many iterations, that iteration result itself is giving a reasonable good results, I will choose those results. So, depends on the whether we have freezing 0.46 or 0.45, we can find out attitude angle, and attitude angle for 0.45 is turning out to be 57.3 degree, which is a higher value. We can increase this, we can change the bearing length, we can reduce the bearing length, we can change the parameters, so that eccentricity is coming out to be 0.7.8. That will be the more desirable level. That is giving an indication bearing length increasing from 10 mm to 20 mm is not fulfilling the purpose. Eccentricity ratio is going down. It is more like we have a capabilities, but we are not doing our best. We are not giving our best performance. So, bearing has a lot of capabilities, but because of the larger length, bearing is not able to give this best, which is not desirable. First thing is increasing going for the larger bearing length, naturally cost of the manufacturing is going to be increased, cost of the material is going to increase. In addition, there will be some sort of misalignment. In addition, there will be friction force. I use a word, there will be additional friction force, but we need to check it. We say that for this if I assume 0.45 as a freezing point, calculate what will be the maximum pressure. For that purpose we require theta O max or theta 0 max, and that is turning out to be 110 degree. 110 degree in this case, that is going to give me a value of something like a P max as a 13 bar or 1.3 megapascal. If you remember, the length was 10 mm, this pressure, maximum pressure was only 0.7 megapascal. So, what we are doing, increasing the bearing length, maximum pressure has been increased to 1.3 megapascal. One way it is a negative side, by the way we say that okay, bearing material mostly they are able to sustain more than 5 megapascal. So, why to worry about 1.3 megapascal, let it be like that. If bearing length is giving all other advantages, we should go ahead with a larger length, but temperature rise from a coefficient of friction point of view, say that coefficient of friction in this situation, because friction force is a 7 Newton in this case divided by 600 is going to give us a result of 0.0117. Coefficient of friction is a 0.0117, while in earlier example this coefficient of friction was lesser than this 0.0086. So, increasing length is not fulfilling a lot of purposes. First, eccentricity is going down lesser than, we say that 0.5 may be recommended fine, but that is increasing maximum pressure. Larger length is giving lesser pressure compared to, smaller length is giving larger pressure, smaller pressure compared to larger length, which is a quite reverse. While coefficient of friction for the smaller length is lesser than larger length. Naturally, I will prefer a lesser length, smallest length for the bearing it saves a space, save the cost, gives optimum performance, and that is the what we gain from studying lubrication mechanism, understanding tribology. Otherwise, if somebody says the load carrying capacity is okay, we'll go ahead with the maximum length. That is a wrong. Here, lesser length, smaller length is giving more benefits, lesser maximum pressure, lesser coefficient of friction, lesser space, lesser cost. So, that is essential for us. Obviously, that is going to give us overall economics. So, with this, I am trying to close the course. I hope you understood the course, and in future you will be able to save a lot of cost incorporating tribological principles, tribological guidelines. Thank you for your attention.